Hello everyone. Today in this lecture we discuss about topic matrices. First of all we discuss what is matrix. See, the matrix of order m cross n is a square arrangement of m square elements. Means if matrix is 2 cross 2 then it is square arrangement of 2 square elements, that is 4 elements. So we will discuss some matrices of order 2 by 2 and 3 by 3. See, this is a matrix of order 2 by 2. This is a matrix of order 3 by 3. These are two matrices. This is of order 2 by 2 and this is of order 3 by 3. These are called as square matrices. Generally, we denote matrix by using capital letters. Consider here matrix A is equal to this 3 by 3 matrix 1, 2, 3 minus 1, 0, 2, 3, 1, 0. This is one 3 by 3 matrix. Now we discuss about elementary transformations. There are three types of elementary transformations. First is interchange of any two rows or any two columns. We will discuss these elementary transformations for matrix A one by one. So first transformation is interchange of any two rows or any two columns. So for transformation A, see, interchange of any two rows. Suppose we interchange R1 and R2. We denote rows by R1, first row by R1, second row by R2, third row by R3. So if we consider here operation interchange of R1 and R2, then we denote this operation by R1 interchange with R2. So matrix A is converted to write R2 in place of R1 and R1 in place of R2. So our converted matrix is minus 1, 0, 2, 1, 2, 3, 3, 1, 0. Suppose if we perform this operation for column, suppose C2 interchange with C3, then we get C1 will remain as it is, 1 minus 1, 3. We are considering these operations on matrix A only, not on this converted matrix. So for matrix A, C2 interchange with C3 is 1 minus 1, 3, 3, 2, 0, 2, 0, 1. This is first elementary transformation. See, second elementary transformation, you can see here. Multiplication of the elements of any row or column by a non-zero scalars. Means we select one row and multiply each element of that row by a non-zero scalar. So if we consider operation R1 changes to 3 into R1 in matrix A, we get R1 changes to 3 into R1. So we multiply each element of R1 by 3. So 1 into 3 is 3, 2 into 3 is 6, 3 into 3 is 9. Remaining elements are as it is. This is second elementary transformation. Third elementary transformation is adding the scalar multiple of all the elements of any row or column to corresponding elements of any other row or column. So, if we consider this matrix A and operation R1 changes to R1 plus 3R2, means we are adding multiple of R2 to R1. We will multiply row 2 by 3 and add it to R1. So our resultant matrix will be Here R1 is changing because we are adding multiple of R3 to R1. So instruction is R1 changes to R1 plus 3R2. So R1 will change. So R2 and R3 remain as it is. So first element of R1 will be 1 plus minus 1 into 3. So 1 plus 3 into minus 1, which is equal to 1 minus 3 is equal to minus 2. Second element will be 2 plus 3 into 0. 2 plus 3 into 0, which is equal to 2 itself. Third element will be 3 plus 3 into 2. 3 plus 3 into 2, which is equal to 3 plus 6, which is equal to 9. So this is result of R1 changes to R1 plus 3R2. These are three elementary transformations which we are going to utilize in this topic. Inverse of a matrix. If A is a square matrix of order m, note order of A is m, and if there exists another square matrix B of the same order, means order of B is also m, such that AB is equal to BA is equal to I, where I is identity matrix of order M. Here M is order of original matrix A. Then B is called as the inverse of A and it is denoted by A inverse. In this topic we will discuss how to calculate inverse of a matrix. Now criterion for invertibility. A square matrix A is invertible if and only if the square matrix A is invertible if and only if determinant of A is non-zero. That is, if we want to find out inverse of any matrix, then first of all calculate its determinant. If determinant is non-zero, then proceed to calculate inverse. If determinant is equal to 0, then we may say that this matrix is not invertible matrix. Now next point, if A is a square matrix, if A is a square matrix and its inverse exists, then it is unique. Means any matrix can have at and one and only one inverse. Next, now we discuss two methods for calculating inverse of a matrix. First method is inverse of a non-singular matrix by elementary transformation. What do you mean by non-singular? Non-singular matrix means its determinant is not equal to 0. Matrix whose determinant is non-zero, it's called as non-singular matrix. So first method is by elementary transformation. We will discuss this method. First of all, we discuss one problem. Calculate inverse of non-singular matrix by elementary transformation. Either we apply row transformations or column transformations. So, if we are applying row transformations on both sides of the equation, then use equation A into A inverse is equal to I. Then apply row transformations to convert this element A to identity matrix. Okay. And apply row transformations applied on A to this identity matrix I on right hand side also. Now if we are going to operate column transformations, then consider equation A inverse into A is equal to I. Apply column transformations on matrix A present on left hand side. Apply same column transformations on identity matrix I present on right hand side and get A inverse. So we will solve one problem by using elementary row transformations. The problem: find the inverse of matrix 1, 2, 3, 1, 1, 5, 2, 4, 7 by using elementary row transformations. So First of all, we will check this matrix is invertible or not. So we will calculate its determinant. So this is calculation for determinant of matrix A. Finally, we get determinant is not equal to 0. Therefore, A inverse exists. Now in question, we are asked to calculate determinant by using row transformations. Therefore, we consider the equation A into A inverse is equal to I, this equation. So, consider A into A inverse is equal to I. Now, we try to convert this matrix A, substitute value of A in this equation and try to convert this matrix A to identity matrix by applying row transformations. For this, one process is given. Reduce A11 to 1. First reduce A11 to 1. Then reduce A21 to and A31 to 0. Means first of all reduce, if this is your matrix with this 9 entries, this first of all reduce this element to 1, this to 0, this element to 0. Next A22 to 1, this element to 1, then these two elements to 0. After that convert this element to 1 and other two elements to 0. So we apply this procedure C. Here if you observe, this element, first row first column element is already 1, so no need to convert it. So now we will try to make these two elements as 0. So if you observe carefully, if we subtract R1 from R2, then we get 0 at second position in a first column. So our operation is R2 changes to R2 minus R1. We get, apply same operation on both matrices, on A also and on identity matrix also. Now we try to convert this element to 0. So if we subtract 2 times R1 from R2, then this element will become 0. Next operation is R3 changes to R3 minus 2R1. Operations which we are performing on A perform same operations on this identity matrix also. So now we check next operation. Now we want to convert this middle element to 1. Think which operation we can perform. If we multiply this minus 1 by minus 1, we get 1 here. So our next operation is R2 changes to minus 1 into R2. So result is 1, 2, 3. Minus 1 into 0 is 0. Minus 1 into minus 1 is 1. 2 into minus 1 is minus 2. 0, 0, 1 into A inverse is equal to 1, 0, 0. Minus 1 into 1 is 1. 1 into minus 1 is minus 1. 0, minus 2, 0, 1. आपलं ऑपरेशन -1 इंटू R2 असल्यामुळे फक्त R2चे जे एलिमेंट्स आहेत त्याला आपण -1 ने मल्टिप्लाय करणार. नाव our next aim is to convert these two to 0. So our next operation will be R1 changes to R1 minus 2R2. C 1, 0, 7, 3 plus C 3 plus minus 2, 3 minus 2 into minus 2, which is equal to 3 plus 4, which is equal to 7. So here it is 7. Next two rows are as it is. Applying same operations on matrix on right hand side, we get this matrix. Now to make this 7 to 0, we apply operation R1 changes to R1 minus 7R3, we get. Now to convert this minus 2 to 0, we use operation R2 changes to R2 plus 2 into R3. Performing above operation, we get this matrix. Apply same row operations on left hand side and right hand side also in each steps. This is identity matrix. So identity matrix into A inverse is equal to this matrix. So A inverse is equal to this. So our solution is completed. For solving problem using column transformations, use same column operations.